joint work with my advisors, Ruslan Salakutinov and Sergey Levin. Arguably, much of the success of supervised learning is that it just works. Users can provide some task, maximize some objective function, and be pretty sure that the learned model will make reasonable predictions on most inputs that are like the training examples. In contrast, reinforcement learning is often viewed as brittle. Learned policies don't work well on environments that are even slightly different from the training environment. And it's often really hard to guess what the learned policies are going to do. This talk is about how a simple idea from compression can make RL policies more robust and more predictable. In supervised learning, it's well known that compression is very closely related to generalization and robustness. We say that a model is compressed if the model's output is a simple function of its inputs. In the field of compression, there are many different methods for doing compression, some of which are much better than others. In this paper, we explore how strong compression algorithms can yield very robust policies that generalize broadly, and even end up learning models of the world. But that's getting ahead of the story. To start, we need to review a bit of compression. Let's say that you have a message that you'd like to send, and it consists of 4 words. One way to send this message is to encode each word separately. A good code will use shorter code words to send more common words, and longer code words to send less common words. For example, the word the is very common in English, and therefore should be assigned a short code word. One way to think about the code is as specifying what words the receiver expects to receive. However, if you're sending a long sequence of words, you actually can do better. Rather than encoding all the words in the same way, always using the same code for the same word, you can use the words you've already sent to change how you'll encode future words. This idea is sometimes referred to as online coding. The intuition behind why this is useful is that receiving some words should change your prior belief about the likelihood of receiving other words. So while the word the might be very likely a priori, if you've already received the word the, you're pretty unlikely to receive it again, because the sentence the doesn't make any sense. Now, one interesting feature of online coding is that it effectively learns a model of code words, a model that guesses what the next code word will be given the previous code words. In general, online coding can work a lot better than encoding all words independently. So what would it mean to apply compression to reinforcement learning? We will look at the input-output relationship between states and actions, and we want the actions to be a simple function of the state. Importantly, we'll look at not individual states and actions, but rather the entire sequence of states and actions. And in fact, we want the agent's temporally extended behavior to be simple. We will measure compression of the policy using the mutual information between sequences of states and sequences of actions. The degree of compression will depend on the data distribution. And in the RL setting, the agent actually gets to choose the data distribution, so the agent may change its behavior to become more compressible. To learn compressed policies for reinforcement learning, we'll maximize reward while minimizing the amount of information used. And there are many ways to maximize this objective. Prior work has looked at a couple different ways. In this paper, we apply a more powerful compression algorithm, online coding, to optimize this objective. The result is a tractable objector, which is a proper lower bound on the original objective. And because we're using a more powerful compression algorithm, this bound is tighter than prior work. We call our method robust predictable control, because it'll end up learning policies that are both robust and predictable. This objective can be understood as a modification of the standard RL problem that uses a different reward function. And this reward function depends on 3 components: a policy, a latent space model, and an encoder. Note that the policy, the latent space model, and the encoder are all optimized using the same objective, and this makes implementation very easy. To understand how these components interact, let's look at a diagram of the method. Robust predictable control, or RPC for short, learns these 3 components: the encoder, the policy, and the latent space model. The encoder compresses observations into compact representations, and the policy chooses actions based on those representations. Now, the most interesting part is this model that predicts the next representation, and this is just like in online coding. The encoder and the model end up being trained to be self-consistent. That is, the output of the blue arrow should equal the output of the green arrow. And the policy is trained to maximize reward while visiting states where the latent space model is correct. Because if the policy can visit states where the model is correct, it needs to look at fewer bits of the observation. Thus, the policy is also trained to be self-consistent with the model. At this point, we've introduced the method. I want to step back and explain 2 different methods for understanding RPC, which will help build some intuition for what it's doing. One way to understand RPC is to compare it to a variational information bottleneck. An information bottleneck will map each input to a representation that's close to some prior. Now, you can interpret RPC as predicting that prior. Thus, RPC can be interpreted as making the information bottleneck tighter by exploiting the sequential nature of the problem. Another way to interpret RPC is that it changes the reward function to make the agent pay for bits of observation that it observes, and it does this by subtracting them from the reward function. However, if the agent can successfully predict the next action, then it doesn't need to look at the next observation at all, and it avoids paying anything at the next time step. Importantly, because the agent has to pay for all of those bits that it fails to predict, the agent will actively change its behavior to become more predictable. So if, say, a task can be solved in multiple ways, our method will prefer solutions where the agent's model can more accurately predict the future. Thus, the second mental model for RPC is that it is a model-based RL algorithm. However, unlike prior work, our method rewards the policy for going to states and actions where the model is correct, thus avoiding model exploitation. Let's try to see how RPC works on some experiments. We compare our method to a number of baselines in a very challenging setting, solving continuous control tasks using policies that can only look at a very small fraction of the observation, from 0.1% down to much less than that. One baseline uses a standard information bottleneck. Another uses an information bottleneck and a modified reward function. Our method, shown in green, achieves rewards that are up to 5 times better than these baselines. And this experiment is run when all methods look at the exact same number of bits. RPC changes the agent's behavior. In this driving task, the RPC agent is less aggressive and passes fewer cars. And this makes sense. Passing cars is a delicate maneuver that requires many bits of information about the positions of other agents. In fact, if we plotted the number of bits that the agent was observing, we would observe that the number of bits spikes when the agent gets within 15 meters of other cars. RPC not only changes the agent's behavior, but also changes the representations learned by the agent. In this plot, we show how many bits are stored in each coordinate of the agent's representation. If we do standard RL, performing no compression, then the agent encodes many bits in every coordinate. In contrast, RPC learns a sparse representation, using only a handful of coordinates to communicate information about the state. Now, the ways in which compression changes the agent's behavior have some important practical benefits. These benefits include better generalization, robustness, and skills for hierarchical RL. Let's look at these benefits in detail. First, because the policies learned by RPC use fewer bits of information about the environment, we expect them to be more robust to changes in the environment. If, say, we increase the mass of the agent or decrease the friction of the environment, we observe that the compressed agents continue to perform well, generalizing well to these new dynamics. Similarly, because the policies learned by RPC use only a few bits of information, we expect them to be less exploitable. In this experiment, we performed adversarial attacks on the agent to make it perform poorly. If we perform standard reinforcement learning, the learned policy would be quite brittle, performing poorly under such attacks. However, the policies learned by RPC are much more robust. These first two benefits of RPC, robustness to changes in the environment and adversarial attacks, don't require the learned dynamics model. But the learned dynamics model is useful in a few ways. One way to look at the learned dynamics model is that it allows the agent to decode the representation. So if we have some representation, we can use that to predict the current action, but we also can use it to predict the next representation, from which we can predict the next action, and so on and so forth. Thus, these representations provide a temporally extended representation of behavior. We can use these temporally extended representations as a sort of option or skill in a couple different ways. Perhaps a simple way to use these options is to choose actions when the agent's sensors are broken. In this experiment, we turn off the agent's sensors after a few time steps. We compare to a baseline that trains the agent using standard RL and then fits a state space model to the environment. This baseline takes actions that are very hard to predict, causing it to choose bad actions and flip over. In contrast, the RPC agent has trained the policy to be self-consistent with the latent space model. And therefore, it keeps choosing reasonable actions when the sensors are broken, enabling the agent to keep running. In the end, the RPC agent runs about 40 times further than this baseline. When we evaluate RPC in settings like this with broken sensors, we observe that the policies learned by RPC outperform those learned by a number of alternative methods, including those that learn different types of models and those that use RNNs. Now, another way to use the open loop options learned by RPC is for hierarchical reinforcement learning. To do this, we first apply RPC to one training task. Then we can plan over these representations to solve a new task, and this new task might involve composing some of the skills learned to solve the training task. In one experiment, the training task was this pushing task, and the testing task added a new obstacle to the environment. Our experiments showed that performing hierarchical RL using the skills learned by RPC worked well, outperforming a number of prior methods and other baselines. In summary, the main idea of this paper is to use ideas from compression to learn RL policies that are both robust and predictable. A key takeaway from this paper is that the compression provides a simple way to learn self-consistent models. And as model exploitation is a major problem for today's model-based RL algorithms, this self-consistency might be a useful tool for building new and more robust model-based RL algorithms. Also, insofar as better compression gives better robustness, looking for even better compression methods might provide even more robust policies. We've released code for RPC. Please stop by the poster or get in touch to chat more about RPC and future work. Thanks.